Good day, everybody, and welcome to this channel. Today's video is a continuation of the previous video I made about compression members, where I covered some of the theory around buckling and effective lengths, etc. So in this video, we're actually going to do a design example. So here we have to design a universal column, commonly referred to as UC section, of length 4 meters with no lateral restraints to carry a concentric ultimate compressive design load of n star equals 500 kilonewtons. Right. So before we start diving into solving this, let's just break down the question and what what it means. Right. So what I mean by a pinned universal column is a column that has pinned ends, right, at the top and at the bottom, and this means that translation about translation is fixed, but rotation is released. Right. So the way we denote this is we can say F, 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 and then R, 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 where the first three terms stand for translation, right? First three terms cover translation, and then the next three are about rotation. Okay, so this is translation along X, translation along Y, translation along Z, and these are all fixed, but rotation about X, rotation about Y, and rotation about Z are all released. So that's that first term. Um, the second aspect of this question is what a universal column section is, right? So in Australia, this design example is going to be to AS4100, which is Australian design code. So we have standard sections in Australia, and one of them is a universal column. So we have, as you can see in this list, we have welded beams, welded columns, universal columns, tapered flange, parallel, etc. Right? But the most common ones you'll see are universal beams, universal columns, parallel flange channels, equal angles, unequal angles. These are the ones we deal with most of the time, although in some situation you can also encounter these other ones, right? So in this example, we're going to be focusing on universal columns, and the way that looks like is, so let's go to page 16 of the catalog. It's welded columns, universal beams. Here we have universal columns, and as you can see, it's an eye shape. Okay. The length of the column is 4 meters, and it has no lateral restraints, so nothing stopping it from moving side to side. And then we have to carry a compressive load of n star equals 500. So this, in practice, this design action you'd get from your software or however you've calculated it. So in this case, we're dealing with n star 500 kilonewtons, so that's factored. So we're not applying any factors to it. We're not multiplying it by 1.2 or 1.5 or whatever. So we're going to leave that as it is, and we're going to design for that load in this case. Okay, so let's dive into the example now. We're going to use an equation to find an approximate moment of inertia about the y-axis, and this will help us pick a section to start with, design that, and then if that's not sufficient, we increase the size and keep iterating like that. So we'll start with the buckling equation, which is nominal buckling equation equals pi squared EI divided by LE squared. Now you have to make sure that this moment of inertia here is actually IY, which is second moment of area and of area about y-axis, or commonly referred to it as the minor axis as well, or the weak axis. Okay. So this is, if you have an I section like this, right, this here is the major axis XX, and this is the minor axis YY. So that's something to keep in mind. Okay, now, so in this, from this equation here, you can see that we have this as 500, or we obviously know pi is 3.14, and we have E, which is a constant, 200,000 MPa, and then we also have effective length here, and then we have we just have to solve for IY. So basically what we have to do is rearrange this equation so we can bring our iy here. Okay, so that's going to be iy equals times le squared divided by pi squared over e times e. Okay, now you might be wondering what is LE, all right? That's the effective length, right? Here I've mentioned here that the length is 4 meters, but I haven't said that the effective length is 4 meters, and there's a difference, right? The effective length of a member LE equals KE times L, where KE is the effective length factor. Effective length factor, which you can, according to the code, Australian code S4100, is factor that you get from idealized column configuration. Say, for example, if you have a pinned column like we have here, KE equals 1 in our situation. If you have a column with fixed ends, right? So fixed ends meaning your translations are fixed and your rotations are also fixed in all the directions. So that's KE is equals to 0.7. Right? If you have one end is fixed and the other end is pinned, you're going to have KE equals 0.85. And then if you have a fixed end and the other end is totally free, your KE equals 2.2. All right. So the effective length factor here is highest, 2.2, which is going to increase your effective length, which is basically 2.2 your effective length will be basically 2.2 times the length of your member. So in this example, it would be 8.8, right? But in this example here, we don't have to worry about that one. Our effective length here is going to be KE equals 1. And so the effective length is just going to be still 4 meters. All right. Now, we have the effective length as 4 meters. We have and star is 500 kilonewtons. We have E as 200,000 MPa. Therefore, we can plug these into the equations, into this equation here, and we can solve for IY. Okay, so IY equals M times, IY equals 500 times 10 to the power 3 times 4 times 10 to the power of 3 squared divided by pi squared times E. All right, so let's plug this into the calculator and see what we get. IY equals All right, as you can see there, we got IY equals 4.053 times 10 to the power of 6 millimeters. It's about 4. Now, in case you're wondering why I got this from here, times 10 to the 3 times 10 to the 3, is because a lot of people get confused with the units when they're working with these sort of equations. And typically we want to work in newtons and millimeters in the equations, and then at the end we can convert to kilonewtons or kilonewton meters when you're calculating moment. So in this case, we kind of want to we want to stay we want to work here in newtons, and we also want to work here in millimeters to avoid confusion. Okay. Yeah, so IY here is 4.053 times 10 to the power 6. Now, the next step is to go to the universal column section catalog and check for the values of IY and look for something that look for a still section that will closely match 4.05 times 10 to the power 6 millimeter to the power 4. Okay. Now here we have, what do we have? I'm gonna close this calculator for now. We're going to have a no, this one doesn't cover. All right, it's up here. Okay, so here we have about y-axis. We can look at the moment of inertia, which is IY. About the y-axis, here we have 3.98, which is not enough, so we have to pick 5.62, and that corresponds to a 150 UC30. All right, therefore adopt 150 UC 30, right? Because this has the next closest moment of inertia up. Right. Now, let's solve for the section capacity of the compression member 150 UC30. So phi ns, which is the section capacity of compression member. That's equal to phi times kf times an times fy. That's equal to 0.9 times 1.0 times the net area here, because we're assuming that we don't have any holes in our cross section, so the net area here will just be the gross section area, AG, which we can also get from the one steel catalog table for 150 UC30, which is 3860. So times 3860 times we have fy as well. Usually these values are a bit higher, but we're going to work with 300 MPa. Okay? So that gives us 0.9 times 1.0 times 3860 times 300. And also here, be cautious, like I said before, we're going to work in millimeters square here, and we're going to work in MPa here. and this will help us keep our units consistent. When we multiply these, we'll get our answer in newtons, and then we can later convert that to kilonewtons. All right, so we have 1042.2 times 10 to the power of 3 newtons. Okay, and then to convert from newtons to kilonewtons, again we have to multiply by 10 to the negative 3. So answer is, so that basically just cancels that, and then we're going to have 1042 kilonewtons. Right. Okay, before I move on, I want to quickly touch on KF, which in this case equals 1. So because we're dealing with universal column sections, you're not going to have to worry about KF. That's because if you come here to the catalog, KF values for universal column sections are all equal 1, and KF is the form factor. So what is the form factor KF? KF is equal to effective area over cross section area. So it's a ratio of the effective area over the cross section area, so which is the sum of plate elements, okay, effective width times thickness, and then again divided by the cross section area, elements B times T. And by plate elements, what I mean is if you have a universal column like that, ignore my poor drawing skills, but what we have here is you can take each flange outstand as a plate element, and the web here is another plate element. Okay, so we have plate 1, 2, 3, 4, and the web being the 5th plate element. Okay. Right, so what is effective with BE? BE equals B multiplied by ratio of lambda EY divided by lambda E, and lambda EY in this context means plate slenderness limit. Okay, slenderness limit, and lambda E is the plate element slenderness. Okay, slenderness. Lambda E, so lambda EY, you can get this from the code, right? And it essentially depends on how your flange is supported. So is it only one edge is supported, or both edges are supported, and is it hot rolled or is it cold form? It just depends on that. But what's really going to drive your and then the other factor that's going to drive your effective width is the plate element slenderness, lambda E, which is essentially B over T multiplied by the square root of A Fy divided by 250. Okay, Fy in this case is 300 MPa, so that's fine. But you can see here I have another ratio, B on T. Okay, so B on T really B on T is going to drive what your slenderness is going to be, and that slenderness is going to affect your effective width. The effective width is going to affect your effective area, and then that's ultimately going to affect this ratio. But let's backtrack again, okay? Let's say you have a section that has a high B on T ratio. What happens in that case? That means that the plate elements are much wider than they are thinner. Okay, So if B on T increases, lambda E also increases, and when B on T increases, lambda E increases, and then when lambda E increases here, what happens? This whole fraction goes down. And when this fraction goes down, ultimately your effective width reduces. And then when your effective width reduces, what you're going to end up with is a ratio here that's going to start being less than 1. Because this cross-section area is only going to change, is only dependent on the geometry of your plate. But this here, the cross-section area here is not going to be affected by the slenderness. That just always stays as the section is, but this one here is really affected by the ratio of the plates. So like I said, if you have a high B and T ratio, you get a high lambda E, you get a high lambda E, you get a lower effective width, you get a lower effective width, you ultimately get a lower effective area, and your form factor becomes less than 1. And what happens when this form factor becomes less than 1? Ultimately, your section capacity of the compression member goes down. Okay, so that was a bit of a detour. And if I go back to the steel catalog, okay, here you can see that universal column sections have a form factor of all of them are 1, sorry. All of them are equal to 1. And then if I come here to universal beams, you can see here that the form factors, some of them are 1, but as soon as you get past 250 UB, they're all, less than 1, right? So that means that the section capacity gets reduced a little bit. Now the reason for this is this picture, actually, if I zoom into these two pages here, this is the pages for UB and UC. What you'll notice here is that UBs are typically long and narrow, so the web is very long and the flanges are narrower. And UC section, universal column sections, you can see here that these are, pretty much almost equal, right? Look at these values. Look how close they are together. You have a width of 311 and a depth of 327. So these numbers are super close together. But then if you come to universal beams, these numbers are far apart. Sorry, wrong one. These numbers are a bit different, right? They're a lot deeper than they are wider. Okay, so what that means is that UB sections will typically have a higher B on T ratio than UC sections. And that B on T ratio you can get from here, right? So that's the B on T ratio for web, and then that's the B on T ratio for flange. And you can see universal beams here have higher values of higher B on T values than universal column sections, right? Here we're dealing with the highest being 28, but here your highest is like 54, right? So that's why universal beams have reduced form factors, so form factors less than 1, but universal columns have form factors equals to 1. Okay, so that's just something to keep in mind. Now let's get back to this. The member compression capacity, NC equals alpha C times NS. And because we've already reduced the section capacity by this phi reduction factor, which is 0.9 for this kind of failure, we don't have to do that again over here. So just keep that in mind. Now, what is alpha C? we should also write this up here. So member compression capacity. So alpha C here is the slenderness reduction factor. Okay, slenderness reduction factor, and this is calculated. There's a few factors that go into calculating this. The first one is you need to know what the modified slenderness ratio lambda n is. So this is the modified slenderness ratio, and lambda n in this case equals LE over R multiplied by KF, which is the form factor, Fy divided by 250. Okay. In this case, we know everything here, right? We've said that LE from over here equals to 4 meters. We know that R is the radius of gyration about the minor axis, and that's a factor that you can get from here. Where is it? Ry you can get from that's universal beams. Let's go to universal columns. Ry you can get from here. Okay, but in this case we're dealing with a 150 UC30, so if I track that across, that's going to be 38.1. Okay, so we have lambda n equals remember, we're going to work in newtons, millimeters. Newtons and millimeters, always remember that. So we have 4 meters, which is basically 4,000 millimeters. Then we have 38.1, I believe. Yep, 38.1. And then multiply that by the square root of 1.0 times Fy, which is 300, divided by 250. Okay. And that should give you 115.01. Once you've calculated your modified slenderness ratio, you need to calculate alpha B, which is a section constant. Okay. And in this case, it's equal to 0 because we have hot rolled. So we have cause 6.3.3, which is right here, and we have a hot rolled UC section, which has a flange thickness of less than 40 in this case. So alpha B for us is going to be 0. Okay. So alpha B equals 0. And that one is a hot rolled UC less than 40 millimeter thick flange. Okay, so that came from. Now, alpha C is a function of the slenderness and alpha B, and you can get that here from the code. If I scroll down a little bit more, you can see that the values of member slenderness reduction factor alpha C is dependent on alpha B and lambda n. Let me do this in a different color to make it more distinct. So you have alpha C is dependent on alpha B and lambda n. In this case, we've said lambda n is 115, okay, and alpha B is 0. Alpha B is 0. So if we come across this way, you can see we have 0.448. So our factor alpha C equals 0.448. then the member compression capacity NC is going to be 0.448 times NS, which we calculated before, which is 1042. So 1042, and that should give you 466.9 kilonewtons. Now, that means that our member compression capacity is 466.9 kilonewtons, but we have an N star of 500 kilonewtons. So the capacity is actually less than the action, which means our member fails. So that's less than N star, and it's not acceptable. Okay. Acceptable. So what do you do in this case? You can increase the size of the member, right? That's the first step. That's what we're going to do. Let's backtrack again. Let's look at what members are available to us, what members we can go up to next. All right, so we have universal columns, and the next one up is 150 UC 37.2, which I can try, but just to be on the safe side, I think I want to go one up on top of that. This is where the iteration process comes in, okay? So instead of doing all this by hand, what you can do is you can use software programs, you can use Excel sheets, and things like that, just to automate this process of iteration, because it can take a lot of time. Yeah, so in this case, we can go up to the next section of, we can go up actually two sections, which is 200 UC 46.2. This one over here, all right, change different color, which is that one over there. Go up another section, and this is where the iteration process comes in. You can use Excel sheets to automate this process instead of having to calculate again by hand, which can save you a lot of time. So, but for the purposes of this tutorial, I wanted to go through the whole thing. I'll try another section up, another couple sections up. I'll move to 200 UC 46.2, okay? Which I'm hoping, pretty sure it should work, but we shall see. So we have I'm going to say here is try using 200 UC 46.2. Yeah. Now the phi and s for this is equal to phi kf an fy, and we've said that's 0.9 times 1.0 because it's a UC, and then an, which is the net area, but because we don't have holes, we're just going to take the cross section area. So that's 5900 times 5900 times 300 MPa, which in this case gives you 1593 kilonewtons, and then NC equals phi NC equals phi and s alpha c. So alpha c, again, like we said, is dependent on the slenderness, dependent on the modified slenderness ratio alpha lambda n and the section constant alpha b. Okay, so lambda n equals LE on R multiplied by KF Fy divided by 250. 250, and we said we know that's 4,000, and the y, because we're dealing with the minor axis here, for that section should be 51.0. Okay, 51.0. Oops. 51.0 multiplied by 1.0 times 300 MPa divided by 250. I'm just going to quickly do this on the calculator here. It's 4,000 divided by 51.0, square root of 1.0 times 300 divided by 250. That gives us 85.9. 85.9. And we know alpha b is not, that's not going to change, that's still 0 because our section is still hot rolled, and yeah, our section is still hot rolled and still has a flange thickness of less than 40. Well, alpha c, we can go back to one steel tables and look, sorry, not one steel tables, the code, and look for a slenderness ratio of 85. That gives us 0.645. And one thing to keep in mind here is our slenderness ratio is actually not 85, it's 85 point something, 85.9 in this case, so we have to interpolate between these, okay? And what interpolation basically means is just take a value between these two depending on what you calculated. So we have 85.9 here, and we have to find this value here, alpha c, okay? And the way I like to do this is I take kind of take it as coordinates and trying to find the gradient and solve for get the gradient and then solve for the y coordinate at that point being alpha c. So we have 85, 0.645, 85.9, and then alpha c. This is what we're trying to find. And then we have the next one is 90 and 0.61, 90 and 0.61. So if I try to find the slope of this line here, is we know the gradient equals change in y over change in x, rise over 1, which is 0.645 minus 0.61 divided by 85 minus 90. And if we try to solve for that as well, we have 0.645 minus 0.61 divided by 85 minus 90. That gives you minus 0.007. Then again we say minus 0.007 equals alpha c minus 0.61, and then equals 85.9 minus 90. Okay, then you rearrange and solve for alpha c in this case. So what I can do that is minus 0.0. Sorry, let me just quickly erase that. Alpha c is going to equal minus 0.007 multiplied by 85.9 minus 90, and then divide that number, sorry, add 0.61. Okay. Alpha C then is going to be minus 0.007 divided by 85.9 minus 90 plus 0.61, which gives you 0.639. 0.639, and here you can see that 0.639, okay, 639 is, somewhere between these two numbers, so that makes sense. Okay, so with alpha C being 0.639, phi and C is going to be 0.639 multiplied by the section capacity, which was 1593, and that gives us 0.639 times 1593, which is 1070.9 kilonewtons. Which is greater than 500 kilonewtons. Okay, so this is acceptable. That's fine. So in this case, we can adopt a 200 UC 46.2. I could have also tried maybe UC 150 UC 37.2, but in this case, I just wanted to go with something a little bit higher just to show how much of an increase that is, and that it's actually passing in this case, and it's greater than 500 kilonewtons, which is N star in our case. And yeah, we're happy with that, so yeah, that's acceptable. So in summary, what you do is you rearrange and try to find IY, and then once you got IY, you look at the one still table and get something that's approximately around that region, but you go one up, and then you calculate your section capacity, which is phi times kf times an times fy, an being the cross-section area, but if you have bolt holes or something, you have to subtract that, and fy is obviously 300 MPa in our situation, and don't forget the reduction factor 0.9. okay, that's very, very important. You also always have to keep that in mind. Once you've got your section capacity, what you do next is you calculate your member compression capacity, which is typically a reduction factor multiplied by the section capacity you just calculated. And then that reduction factor, alpha C, is dependent on the modified slenderness ratio and section constant, lambda n and lambda b. Okay, and lastly, you compare your member compression capacity to your design action N star, and then determine whether that section is adequate or not. Alright, so that's the end of the video. Thanks for watching, and I'll catch you in the next one.